Can you believe it? Aliens may have already pinpointed Earth's location, but they'll never reach us, because direction doesn't exist in the cosmos. NASA scientists uncovered a desperate truth. In three-dimensional space, all coordinates are relative, but the problem is, the universe has no fixed reference frame. They can't tell which way is Orion. Even more terrifying, even if aliens are currently tracking Earth's radio signals, the coordinates they receive might point to nothingness. Because the universe is expanding, the moment you transmit a signal, Earth's position has already shifted completely. Imagine holding an ancient map marked with treasure coordinates. After enduring countless hardships to reach the marked location, you discover the entire island and surrounding seas are shifting unpredictably. The map becomes utterly obsolete the instant you set out. This is the fundamental dilemma facing any civilization attempting to navigate the cosmos. We inhabit a universe perpetually in motion. No point remains fixed and unchanging. Earth is not a solitary marble suspended in static void. Instead, it participates in a grand, intricate, and ceaseless cosmic dance. From the tiniest atoms to the grandest galaxies, everything in the cosmos moves, rotates, and races. The fabric of space itself expands at unimaginable speeds. This omnipresent, perpetual dynamic change is the ultimate barrier to all interstellar travel, and the core enigma we explore tonight. First, let's grasp the nature of the universe's dynamic labyrinth. Imagine this labyrinth as an infinitely vast building without a ceiling. Every wall and corridor within this structure moves and rotates independently. The treasure you seek traverses at varying speeds and directions. More despairingly, the labyrinth itself continuously stretches. The distance between rooms perpetually widens. That map you worked so hard to obtain is already outdated the moment you look down at it. You can never be certain of the target's next location. This is the true nature of the universe, a space where all reference points move relative to each other, a realm where no absolute stationary coordinate system exists. Within this dynamic labyrinth, our home planet Earth participates in at least 4 major motions simultaneously. Earth orbits the Sun at roughly 30 kilometers per second. The solar system revolves around the Milky Way's center at approximately 220 kilometers per second. The Milky Way itself hurtles toward the Great Attractor at about 600 kilometers per second. And the cosmic space bearing all this continues to expand at an accelerating rate. The superposition of these 4 motions makes Earth's trajectory through the cosmos unimaginably complex. It's like trying to aim at another wildly spinning horse on a never-ending carousel, while the entire amusement park drifts along a rushing river that itself keeps widening. Now close your eyes for a moment and try to visualize this dynamic labyrinth. Feel the dizziness as all coordinates flow before your eyes. Experience the helplessness of a target always slipping to the next moment. This is the first and most fundamental despairing truth any extraterrestrial civilization must confront in its search for us. In the journey ahead, we will delve together into the 5 core mechanisms of this cosmic dynamic labyrinth. First, we'll examine why the cosmos lacks fixed cardinal directions. All coordinates are relative and ephemeral. Next, we'll reveal Earth's true trajectory through the universe. You'll discover our home has never remained stationary. Then we'll confront the limitations of light speed and the harsh reality of cosmic expansion. Together, they create a chasm in spacetime. We'll also examine the universe's vision-distorting illusions, like gravitational lensing and the invisible hand of dark matter. Finally, we'll explore why even the most advanced superluminal technologies struggle to unravel this dynamic labyrinth's ultimate paradox. Ready? Let's push open this door of understanding. Step into this awe-inspiring yet profoundly despairing cosmic labyrinth. On Earth, we point to a location and say it is there. This there exists relative to the solid ground beneath our feet. We implicitly assume the Earth is stationary, the benchmark against which all motion is measured. Yet the moment we step beyond Earth's bounds, this ingrained assumption crumbles instantly. On cosmic scales, describing any location demands answering one fundamental question: relative to whom? We cannot point to empty space and declare Earth is here, for here itself is a meaningless concept. We must find a reference point for this here. For instance, relative to the Sun. Earth orbits at a distance of 150 million kilometers. But the Sun itself is also moving. Thus, this coordinate is equally transient and partial. This is the cage of relativity, a physical law that imprisons our intuition, yet reveals the truth of the universe. Einstein's special and general theories of relativity utterly shattered Newton's absolute conception of spacetime. In Newton's vision, the universe resembled an infinitely large, stationary stage. All celestial bodies moved upon this stage according to predetermined rules. Time and space formed an absolute backdrop, existing independently of the actors upon the stage. Yet Einstein revealed to us that this stationary stage does not exist at all. There is no universal, absolute frame of reference to measure the motion and position of all objects. Every observer possesses their own unique space-time perspective. Your here and my here may point to entirely different regions of the cosmos. Imagine yourself floating in the boundless, empty expanse of space, surrounded by distant, hazy starlight. Could you tell whether you were at rest or moving at a constant velocity? The answer is you couldn't tell at all, because there is no fixed background for reference. All motion can only be relative to other objects. If an asteroid happened to be nearby, you could say you were moving relative to that asteroid, or that it was moving relative to you. But who is truly the one moving? This question itself is meaningless in physics, because there is no absolute arbiter. This is the core idea of the principle of relativity. Physical laws take the same form in all inertial reference frames. Whether you are in a stationary laboratory or aboard a spacecraft traveling uniformly in a straight line, the results of any physical experiment you conduct will be identical. You cannot detect your own absolute state of motion through any experiment. Let's illustrate this relativity of position with a more concrete example. Suppose you were born and raised aboard a massive generation starship. This starship cruises through space at tremendous velocity. Simulated starlight is projected onto the ship's interior walls. To you, this starship is your universe, your stationary coordinate system. One day, your telescope observes a distant planet. Excitedly, you record its coordinates. These coordinates are relative to your spaceship. But at the same time, an alien astronomer living on that planet also happened to point his telescope toward you. He likewise recorded the coordinates of your ship. These coordinates were relative to his planet. Now the question arises: do the coordinates each of you recorded for the other describe the same spatial location? In the vast majority of cases, the answer is no, because your ship and his planet are likely moving at different speeds and in different directions. The north, south, east, and west you each define are local directions established based on your own state of motion. From the universe's global perspective, these two coordinate systems are likely tilted or even reversed. A more complex situation arises, because the speed of light is finite. The planet you see is its past state, and the alien's view of your spacecraft is also your past position. When both parties attempt to send messages or probes to each other's potentially current locations based on this past light cone information, Tragedy is already inevitable, because the coordinate systems your calculations rely on are fundamentally separate and inconsistent. This relativity of position is the first and most fundamental obstacle. It means you cannot establish a universally standard star chart. Just as different countries on Earth historically used different map projections, resulting in Greenland appearing larger than Africa, every civilization in the cosmos will map out a unique star chart based on its own local state of motion, valid only for a brief period. What one civilization proudly identifies as the galactic center appears to another merely as an insignificant dot on the celestial sphere. Their definition of the Orion Arm may differ drastically from our geometric understanding. This coordinate cage born of relativity renders any broadcast coordinate information, such as the pulsar map of our solar system's location, engraved on the Voyager Golden Record, appears to an alien civilization receiving it, like an antique letter lacking a sender's date or reference frame. They might decipher our position relative to several pulsars, but those pulsars themselves are moving at high speeds, their positions relative to that alien civilization, already worlds apart from our perceived position. This coordinate letter is like writing with a pen on shifting sands. The moment the information is read, the sands have already shifted. The writing has already blurred. What it points to is more a slice of spacetime where we existed in the past, than a definite destination that can be reached. This is the first shackle relativity has placed upon us. It makes us realize that in the vast cosmos, there exists no solid ground upon which all civilizations can stand together. Each of us floats upon our own solitary island of relativity. When we gaze up at the night sky of the northern hemisphere, the North Star, with its almost eternal constancy, has served as humanity's most reliable navigational beacon for millennia, like a silver thumbtack pinned to the celestial dome. All stars revolve slowly around it, granting direction to the lost, bestowing confidence upon the navigator. Yet this constancy we take for granted is actually a meticulously orchestrated cosmic coincidence, a local illusion confined to the solar system's threshold. The reason Polaris appears motionless is simply because it lies almost exactly along the extension of Earth's rotational axis. As Earth rotates daily, its north pole points directly toward Polaris. This is like spinning a top. If its top were aligned with a lamp, then as the top spins, from the top's perspective, that lamp appears stationary. We are that spinning top, and Polaris is that fortunate lamp. But this lamp does not shine for us, nor is it an absolute universal coordinate origin in the cosmos. Let us broaden our perspective. Departing from Earth's tiny vantage point, you will discover a truth that inspires humility. The North Star, or Polaris, lies approximately 433 light-years from us, a distance unimaginably vast on the scale of our solar system. Yet within the Milky Way's disk, it is merely one of our many neighboring stars. Both it and our solar system reside along the same spiral arm, the inner edge of the Orion Arm. We can envision the Milky Way as a vast city. Then Polaris and our sun are like two adjacent buildings on the same street. We use it as our landmark, simply because it happens to be right outside our door and occupies a sufficiently prominent position. Now let's embark on a thought experiment. Imagine you're aboard a spacecraft leaving the solar system and heading toward the center of the Milky Way. After traveling hundreds of light years, when you look back, you'll discover something astonishing. That North Star, once the cosmic reference point, has quietly shifted from its original position on the celestial sphere. Its relationship with surrounding stars has become distorted and altered. The iconic Big Dipper constellation begins to loosen and distort due to the differing speeds and directions of its constituent stars' motion. Much like a flock of migratory birds that once appeared tightly formed, gradually dispersing over time, this is no illusion, but the result of stellar proper motion. Each star possesses its own unique trajectory within the gravitational field of the Milky Way. As we traverse vast spatial distances, this parallax effect combined with the star's own motion completely alters the patterns we perceive in the night sky. Now let us take it a step further and leap directly to the other side of the Milky Way. Imagine, for instance, a hypothetical planet within the Sagittarius arm. There, the sky you gaze upon would be utterly unfamiliar. All your familiar constellations vanish. The Big Dipper, Orion, Cygnus. These patterns that form humanity's celestial legends are either distorted beyond recognition, or obscured by brighter stars, or never rise above the horizon at all. Would there be another North Star? Most likely, yes. Any intelligent species that develops a civilization will instinctively seek out a seemingly stationary point in their night sky. It will use its own North Pole to point towards some fortunate star. That star will become the totem of their civilization, their sacred guiding star. But their North Star, to us, might be nothing more than an inconspicuous dim star in the southern heavens, or even long incorporated into the toes of some mythical constellation we've named. Such is the fairness of the cosmos, and its cruelty. No civilization holds a privileged vantage point. We are all frogs at the bottom of our own wells. Only the size and shape of the well we peer through differ. This locality of the starry sky proves fatal for interstellar navigation. It means all positional information humanity broadcasts to alien civilizations rests upon an implicit premise that they share the same sky with us, recognize the same Big Dipper, and interpret pulsar positions through identical geometric relationships. This is akin to pointing a spoon formation to someone who has never seen the Big Dipper. Using spoon-shaped patterns to guide them, they would only feel bewildered. Even if an alien civilization intercepted the pulsar map carried by Voyager, they would first need to identify which pulsars we were referring to. Moreover, the relative positions of these pulsars in their own sky might bear no resemblance to the patterns we have mapped. Not to mention that these pulsars themselves are moving at high speeds. Their relative positions have shifted over millions of years. Our cherished cosmic coordinates are like road signs built from grains of Sahara sand. After a gust of wind, they vanish without a trace. When we gaze upon the North Star, what we see is not cosmic truth, but a fortuitous projection of our own position within the cosmos. This seemingly eternal guide is in truth a letter written at our solar system's doorstep. A local message never meant to be delivered profoundly reminds us that any civilization's perspective before the infinite cosmos is destined to be partial and fleeting. The Earth beneath our feet orbits the Sun at 30 kilometers per second. This velocity could make a round trip to the Moon in just 8 minutes. Yet when viewed on the scale of the Milky Way galaxy, this speed seems as slow as a snail's crawl. Our solar system, carrying its entire family, races at a staggering 220 kilometers per second around the distant, enigmatic center of the Milky Way. To complete this monumental journey spanning 100,000 light-years takes the solar system a full 220 million Earth years. This time span is beyond imagination. When the first dinosaur laboriously crawled out of the swamps on Earth, our solar system had only just embarked on half of its current galactic year's journey. Since the extinction of dinosaurs on Earth, The solar system has traversed a mere 1,000th of a circle along its galactic orbit. This protracted cycle, known as a cosmic year, defines the fundamental rhythm of the solar system within the Milky Way. We are immersed in an eternal waltz that has lasted billions of years, and will continue for billions more. In this grand dance, the solar system does not journey alone, carries 8 planets, countless minor bodies, and the comet armies of the Oort cloud, gliding together within the Milky Way's gravitational field. Our trajectory is not a simple circle, but a complex orbit with subtle undulations. At times we traverse the dense spiral arms of the galaxy, while at others we drift through the relatively sparse gaps between stars. These periodic crossings may have triggered massive comet showers and climate shifts, multiple times triggering massive comet showers and climate shifts. Yet the solar system's motion is merely a part of this cosmic dance. Over 200 billion stars in the Milky Way each follow their own unique orbital paths. Some stars move in directions similar to the solar system's, like cars traveling side by side in traffic. Others possess highly inclined or even retrograde orbits, like vehicles approaching head-on at an intersection. This independent motion of each star is called stellar proper motion. It signifies that the night sky is not a static mosaic, but a dynamically flowing river of stars. Consider Sirius, the brightest star in the night sky. It moves relative to the sun at approximately 16 kilometers per second. Over tens of thousands of years, its positional shift will be sufficient to completely alter the appearance of its host constellation, Canis Major. At the other extreme lies Barnard's star. This unassuming red dwarf hurtles toward us at 140 kilometers per second. Its celestial velocity surpasses that of any other star. Every 180 years, it traverses a distance equivalent to the moon's diameter across the celestial sky. Such seemingly minor shifts prove fatal in cosmic navigation. Imagine possessing a galactic star chart accurate to arcseconds, meticulously marking each star's precise position at this very moment. Let us pessimistically assume an alien civilization somehow obtained this star chart. Even if they possessed instantaneous travel technology, when they performed a spatial jump using the chart's coordinates, they would find themselves hundreds of millions of kilometers off course. Because light takes time to travel, by the time they received this chart, it was already outdated. The farther information travels, the more its content becomes history rather than reality. For an observer 100,000 light-years away, the entire Milky Way they see is as it appeared 100,000 years ago. The star map they chart records the solar system's position 100,000 years prior. Yet, in those 100,000 years, the solar system has traveled nearly 15 trillion kilometers along its orbit. This distance easily spans the entire diameter of the solar system. Complicating matters further, the Milky Way's rotational speed is not uniform. Stars at different distances from the galactic center possess varying orbital velocities. This differential rotation effect means the galaxy behaves less like a rigid spinning record and more like a pot of slowly stirred thick soup. Matter within it moves at differing speeds. This complex dynamic poses fundamental challenges to any attempt to create a long-term, reliable model of the Milky Way. We cannot precisely predict the arrangement of the stars tens of thousands of years from now, any more than we can accurately forecast the weather centuries ahead. Minor initial measurement errors will be infinitely amplified by the passage of time and complex gravitational interactions, ultimately rendering predictions completely invalid. Therefore, any interstellar map, no matter how meticulously crafted, is destined to become a rapidly outdated historical document, offering nothing more than a snapshot of the universe, observed by a civilization from its specific vantage point at a particular moment in time, this snapshot begins to irrevocably age. The instant it is created, recording the historical trajectory of photons, rather than the current reality of matter. When our radio signals carry coordinates we deem precise, as they traverse the cosmos, the locations they point to are in fact a past that no longer exists, much like attempting to locate modern-day downtown New York City using an ancient Roman map. The basic grid of streets might remain faintly discernible, but every building, every intersection, has been utterly transformed by time. This is the second lesson taught by the Milky Way's eternal waltz. Motion is absolute. Stillness is but a local, fleeting illusion. The star chart we clasp in our hands is merely a ladle of water scooped from the river of time. As we gaze upon it, the river has long surged forward. The universe's dance never ceases. Any fantasy of using a static map to locate another moving target is shattered. By this eternal rotation, planets orbit the sun in nearly circular paths, like a precision cosmic clock. Yet step back and break free from this partial order, and you witness a starkly different dynamic scene. The entire solar system, this vast family, moves as a single entity through the Milky Way's vast expanse. Its speed reaches a staggering 220 kilometers per second. This figure itself is abstract. Let us attempt to translate it into a tangible concept. At this velocity, the journey from Earth to the Moon would take less than 30 minutes. Yet humanity's fastest spacecraft requires several days to complete this voyage. At this speed, you could circle the Earth's equator in just 1.3 seconds. Each day, the solar system traverses nearly 19 million kilometers through the cosmos. This distance exceeds the round trip from Earth to the Sun. Year after year, the solar system gallops across the Milky Way's wilderness, like a colossal generation ship that never drops anchor. And its course points toward the region of our night sky where the brilliant star Vega resides. More precisely, it points toward a specific location within the constellation Hercules, near Vega. This point is known as the heliocentric direction point. It's important to clarify, we are not hurtling straight toward Vega itself. Nor is Vega our final destination. It serves merely as a prominent beacon along our path, like a distant lighthouse guiding ships. But the ship's destination is not the lighthouse itself. In fact, since Vega itself moves through space, our relative position to it is constantly changing. In approximately 12,000 years, Vega will become Earth's new North Star. But that too will be but a fleeting intersection in the vast cosmic timeline. Why does the solar system move at such high speed? This is not due to any special propulsive force, but rather the result of natural equilibrium within the Milky Way's gravitational field. As a member of the Milky Way, the solar system's velocity is determined by the gravitational potential energy of its location. It must maintain this speed to sustain its stable orbit within the galaxy, avoiding a spiral descent toward the galactic center, nor be flung out of the galactic disk. This motion is not unique to our solar system. The vast majority of stars in the Milky Way possess proper motions of comparable magnitude. They orbit along their respective paths, collectively forming the magnificent panorama of the galaxy's rotation. Our solar system is currently traversing a sparse region of gas known as the local interstellar cloud. This cloud spans approximately 30 light-years in width, composed of sparse ionized hydrogen and helium gas. The interaction between the solar wind and this interstellar medium forms a protective bubble around the solar system, known as the heliosphere, which shields us from some high-energy cosmic rays originating in interstellar space. This journey through the medium evokes the image of a submarine navigating the ocean. its bow pushing aside the water ahead, leaving a wake in its wake. Evidence suggests the solar system's motion through the interstellar medium indeed generates a similar bow shock structure, though its precise form remains a subject of scientific debate. Now pause for a moment. Construct this dynamic image in your mind. We do not reside on a stationary planet, but aboard a spacecraft named Earth. This spacecraft orbits a mothership called the Sun, and this mothership, carrying its entire fleet, plows through the ocean of the Milky Way. At 220 kilometers per second, our home never stands still. It is perpetually in flux. This compound motion renders Earth's position in the cosmos a fleeting variable described by complex functions. Any attempt to pinpoint us from distant stars demands precise calculation of this motion function, and this is merely the beginning of the challenge. For the very stage upon which our motion unfolds itself undergoes a grander displacement, we have only just grasped the solar system's rapid traverse through the Milky Way. Yet this motion does not cease at the galaxy's borders. The Milky Way itself is no solitary island adrift in the void. It forms part of a larger gravitational structure. This hierarchical structure resembles cosmic-scale Russian nesting dolls. Each layer is bound by the irresistible gravitational pull of the one above. First comes our immediate home, the local group. This relatively loose family comprises over 50 galaxies. Its gravitational center lies between our Milky Way and the Andromeda galaxy. The Milky Way and Andromeda are the undisputed giants of this space. They are currently approaching each other at a speed of approximately 110 kilometers per second, and will stage a cosmic-scale collision and merger in about 4.5 billion years. Yet the local group as a whole is governed as a unified entity by a larger gravitational structure. This larger structure is the Virgo supercluster. Now it bears a more poetic name, the local supercluster. It encompasses at least 100 galaxy clusters and groups, including our own local group and the vast Virgo supercluster, spanning a diameter of approximately 110 million light-years. At this scale, galaxies resemble luminous plankton drifting through the cosmic ocean, slowly drifting along invisible gravitational currents. Yet this is still not the end of the story. In the second decade of the 21st century, astronomers mapped the motion of thousands of galaxies to reveal an even grander, more awe-inspiring cosmic structure, the Laniakea supercluster. In Hawaiian, Laniakea means endless heaven. This name aptly describes its vastness. Laniakea spans approximately 520 million light-years in diameter. It contains roughly 100,000 large galaxies. Its shape resembles not a sphere, but rather a faintly glowing feather woven from galaxies, or a colossal cosmic leaf. Its veins are filamentary structures woven from galaxies, while its hollow spaces are cosmic voids nearly devoid of galaxies. Our own Milky Way galaxy does not reside at the center of this feather, but rather at the tip of a remote filamentary structure, like a speck of dust dwelling on the edge of a giant leaf. Now let us return to the core question driving all this motion. What force steers the colossal vessel known as Laniakea? Observational data points to a mysterious and powerful gravitational source, the Great Gravitational Source. It lies approximately 150 to 250 million light-years from us, roughly in the direction of the constellations Ophiuchus and Centaurus. The Great Gravitational Source is not a single celestial object, such as a supermassive black hole, though its central region does contain a massive galaxy cluster, the Scutum-Fornax cluster. Its immense gravitational pull stems primarily from an extraordinarily vast overdensity region, an area of exceptionally concentrated matter within the large-scale structure of the universe. This region's total mass may equate to tens of thousands of Milky Way galaxies. Its immense gravitational pull influences the motion of all galaxies within hundreds of millions of light-years, including our own Laniakea supercluster. The Milky Way is hurtling toward the Great Attractor, along a complex gravitational path. At approximately 600 kilometers per second, nearly 3 times the speed of the solar system orbiting the galactic center. Picture this scene. You sit aboard a spacecraft called Earth. This spacecraft orbits a mothership called the Sun. The mothership carries you through a vast stellar city called the Milky Way galaxy. And now you realize, this immense stellar city itself, along with countless other stellar cities surrounding it, floats within a magnificent gravitational river named Laniakea. This river surges unstoppably toward a cosmic waterfall called the Great Gravitational Source. We are both active pilots and passive fallers, swept along by the gravitational terrain shaped by cosmic matter distribution. Yet an intriguing cosmological fact is that due to the universe's accelerating expansion, we may never truly reach the great gravitational sink, like running on an ever-lengthening conveyor belt, where the endpoint recedes at nearly the same pace. This does not alter the fact we are moving within its gravitational field. This grand descent adds a third, more complex and unpredictable vector. Any civilization attempting to locate us from beyond the Milky Way must not only calculate the solar system's motion around the galaxy, but also the galaxy's motion within the local group, and the local group's plunge toward the Great Attractor within the Laniakea supercluster. It's like predicting the trajectory of a speck of dust dancing in a triple-nested whirlwind, whose complexity exceeds the precise calculations of any traditional navigation system. We inhabit a dynamically layered, perpetually evolving cosmos, from Earth's rotation and revolution to the solar system's galactic odyssey to the Milky Way's cosmic plunge toward the Great Attractor. We are never still. We remain that elusive moving target, in the midst of a mad dash. Thus far, we have sketched a picture of Earth's intricate motion within the cosmos, yet all this movement unfolds against a more fundamental and peculiar backdrop. The very fabric of space itself is continuously stretching. This is cosmic expansion, one of the most profound and counterintuitive concepts in modern cosmology. The classic analogy for understanding cosmic expansion is an inflating balloon. Imagine the surface of a balloon being blown up uniformly. On this balloon's surface live many two-dimensional ants. Each ant perceives its own location as the center. As the balloon expands, the ants observe their neighbors moving away from them. Moreover, the farther away a neighbor is, the farther away they are, the faster they recede. This isn't because the ants are actively crawling away on the balloon's surface. Rather, it's because the space between them, the balloon's surface itself, is being stretched. This analogy precisely captures the essence of cosmic expansion. Galaxies are like those ants. Cosmic space is like the balloon's surface. The galaxies themselves are not hurtling through space at high speeds. Instead, the spatial structure between them is constantly expanding, causing the scale between galaxies to stretch apart. This means the universe has no center. Observed from any point, one sees surrounding galaxies receding, and the farther away the galaxy, the faster it moves away. To quantify this expansion rate, astronomers introduced the Hubble constant, which describes the universe's current expansion velocity. The Hubble constant measures approximately 70 kilometers per second per million parsecs. A million parsecs is an astronomical unit of distance, equivalent to roughly 3.26 million light-years. This value implies, in the universe, a galaxy 3.26 million light-years away from us. Due to spatial expansion, is receding from us at a speed of about 70 kilometers per second. A galaxy 65 million light-years away has a recession velocity as high as approximately 1,400 kilometers per second. And when the distance becomes sufficiently great, this recession velocity will exceed the speed of light. Yes, according to general relativity, the expansion of space itself is not constrained by the speed of light. This does not violate physical laws, because it represents the extension of the fabric of space, rather than the movement of information or matter within it. When an extraterrestrial civilization observes us from a billion light-years away, the space between them and us is expanding at over 21,000 kilometers per second. This speed far exceeds the solar system's motion within the Milky Way, and also surpasses the galaxy's descent toward the supermassive black hole at its center. Under these circumstances, even if they precisely calculated all of Earth's complex motions and launched a probe toward our current position, that probe would face a hopeless race. Not only must it chase a high-speed target, but the very runway between it and the target is being stretched at a rate exceeding its maximum speed. This resembles an ant crawling along an infinitely stretched rubber band. No matter how hard it strives, the distance to the endpoint may not only fail to decrease, but actually keep increasing. Cosmic expansion adds the most fundamental and decisive vector to Earth's motion. This vector does not depend on local gravity, but is inherent in the very dynamics of spacetime itself. It signifies that on sufficiently large scales, the structure of the universe is growing increasingly sparse. Those distant galaxies still within our observable range today will one day accelerate beyond the reach of light itself. Their starlight will vanish forever from human sight. The universe's future is one of ever-deepening solitude. When we synthesize all these motions, Earth's rotation and revolution, the solar system's galactic drift, the Milky Way's cosmic plunge, and space's accelerating expansion, we arrive at a sobering conclusion. Earth's position in the cosmos is an ever-shifting, elusive complex function, not a point to be pinned on a static star chart, but a world line winding through an 11-dimensional spacetime canvas. Any attempt to pinpoint us on an interstellar scale resembles trying to track a specific seabird's flight path with a flashlight on a stormy sea. This is an almost impossible task. Our home is not a stationary target, but a moving labyrinth racing across multiple dimensions. In cosmic communication and navigation, light speed is both the swiftest messenger and the slowest chronicler. It brings news from afar, yet every message arrives as a relic of the past. At roughly 300,000 kilometers per second, light traverses Earth's scale in an instant. But when entering interstellar or intergalactic realms, this velocity becomes painfully sluggish. To grasp this dilemma, consider the concept of the light cone. In Einstein's theory of relativity, the light cone defines the entire possible range of influence an event can exert in spacetime. Imagine your current position in spacetime as a point. From this point, a beam of light travels forward in time. The conical region it traces out is your future light cone. It represents all future regions of spacetime you might potentially influence. Conversely, all events in the past that could have influenced you are contained within your past light cone. Events outside this light cone have no causal connection to you whatsoever. They cannot affect you, nor can you affect them. For any observer, the entirety of information about the universe they can access comes from this ever-evolving past light cone. What they ever see is not the present of the universe, but its history. Now let us place this abstract physical concept into a strikingly concrete scenario. Suppose 1,000 light-years from Earth. An extraterrestrial civilization has developed advanced astronomical technology. They constructed an extraordinarily powerful telescope with sufficient resolution to directly observe surface features of exoplanets. One day, they point their telescope toward the solar system and successfully capture an image of Earth. What do they see? They witness not the brightly lit modern cities of the 21st century. Instead, they observe Earth as it appeared 1,000 years ago. Around the year 1024 AD, China is in the Northern Song dynasty. Emperor Renzong of Song reigned. Fan Zhongyan might have been composing his famous Worries and Joys maxim. Europe was in the medieval Dark Ages. Native American civilizations were quietly developing across the North American continent. The Earth they observed was a pure natural planet, free of industrial pollution, devoid of radio signals, and lacking any artificial light sources. What they witnessed was the world of our distant ancestors. This observational data was invaluable to them. They could deduce Earth possessed liquid water, an atmosphere rich in oxygen and nitrogen, and might even detect traces of vegetation through spectral analysis. They would excitedly record the coordinates of this life-bearing planet brimming with potential, potentially designating it as a crucial target for future interstellar exploration. Yet these coordinates, from the moment they recorded it, became a colossal historical misunderstanding. For the coordinates pointed to Earth's position in the Milky Way 1,000 years ago. Yet at this very moment, as we discuss this here, Earth no longer resides at that location. Over the past millennium, the solar system has orbited the galactic center at 220 kilometers per second and has drifted over 70 billion kilometers from that ancient coordinate. This distance exceeds 10 times the diameter of Neptune's orbit. A coordinate calculated based on light from 1,000 years ago carries an error large enough to send any probe flying directly there, straight into utter emptiness. This is the fundamental navigational dilemma caused by the delay of light. The more precise the coordinates you obtain, the more ancient the spacetime slice they correspond to, the weaker the causal link between you and your target becomes. It's like an inescapable spacetime curse. We are imprisoned at the apex of our own light cones. We can look back at the past, yet we can never touch another's present. Any two distant civilizations are reading entirely different, antiquated versions of each other's history books and planning a meeting that can never synchronize, based on the locations of long-vanished kingdoms recorded within. Having grasped the historical coordinate problem caused by the speed of light delay, we now face an even more fundamental obstacle: the very expansion of cosmic space. If light speed delay misaligns us temporally, cosmic expansion erects a nearly insurmountable dynamic barrier. In spatial dimensions, returning to the Hubble constant concept, the universe expands at roughly 70 kilometers per second per million parsecs. This implies a galaxy 100 million light-years distant is receding from us at a speed exceeding 2,140 kilometers per second. This velocity far surpasses the speed of any human spacecraft and exceeds the motion of the solar system within the Milky Way. When distances reach a certain threshold, galaxies' recession speeds will exceed the speed of light. Based on current observational data, all galaxies beyond approximately 14 billion light-years from us already recede faster than light. Their emitted light will never reach us, nor can we ever reach them. These galaxies have permanently exited our observable universe. Now let's simulate the hopeless journey of an extraterrestrial probe. Suppose a highly advanced civilization resides in a galaxy 100 million light-years from Earth. Through some ultra-advanced technology, they miraculously overcome the light speed delay problem. obtaining Earth's precise coordinates at the present moment. Note that this is impossible under actual physical laws, but let us temporarily assume they can achieve it. They immediately launch a superprobe capable of traveling at 99% the speed of light. At the instant of launch, this probe was indeed precisely aimed at Earth's location. Yet, as the probe began its long journey, a silent separation was already inevitable, due to the universe's ongoing expansion. The space between Earth and the alien civilization's galaxy, stretching at a rate exceeding 2,100 kilometers per second. This means that even as the probe approaches us at near light speed, the actual distance it must traverse increases by 2,100 kilometers every second. It's like an astronaut running on a treadmill moving in reverse. The treadmill belt rolls backward at 2,100 meters per second, while the astronaut can only run forward at 2,997 meters per second. The astronaut is indeed moving forward, but relative to a fixed reference point outside the treadmill. His net forward speed is only 897 meters per second. In the case of this probe, it is indeed traveling at nearly the speed of light relative to local space. However, due to the stretching of space itself, its actual relative approach speed to Earth is far below the speed of light. Detailed calculations reveal a disheartening truth. This probe traveling at 99% of light speed, for the vast majority of its journey, may only achieve a net relative approach speed to Earth of a few percent of light speed in certain phases, when the expansion rate of the universe accelerates due to dark energy. The actual distance between the probe and Earth not only fails to decrease, but may actually increase. It forever strives toward Earth, yet may never bridge that final critical distance, even after an exceedingly long flight. When this probe finally reaches the coordinates calculated 100 million years prior, it will find nothing there. Earth will have drifted billions of kilometers away, along with the solar system's motion. Even more devastatingly, bound by the speed of light limit, the probe cannot receive Earth's latest position in real time, can only follow its initial instructions, searching futilely through that empty expanse for a target that no longer exists. Cosmic expansion acts like a silent director, creating an ever-widening chasm between galaxies. Any attempt to bridge this gap is like chasing the horizon. You advance, it retreats, endlessly. This mechanism fundamentally limits contact between intelligent civilizations in the cosmos. Even if a civilization masters near light speed travel, the expanding structure of the universe ensures they, confined to their own supercluster, for a civilization 100 million light-years away, Earth is not merely a moving target, but a perpetually receding mirage forever beyond reach. Now let's conduct a comprehensive thought experiment. Combine all the motions discussed earlier to intuitively grasp the despairingly precise demands of interstellar navigation. Suppose an alien civilization lies 1,000 light-years from us, a relatively close neighbor on astronomical scales. They possess equally formidable observational capabilities and decide to send a probe to Earth. They observe light emitted from Earth and calculate its coordinates based on this. Due to the 1,000 light-year distance, they observe Earth as it existed during the Song dynasty. Yet they understand the existence of light-speed delay. Thus, employing sophisticated celestial mechanics models, they attempt to predict Earth's position a millennium hence. They account for the solar system's orbital motion around the galactic center. Knowing the solar system's velocity is 220 kilometers per second, they proceed with their calculations. During the probe's 1,000-year journey, the solar system would traverse an astonishing distance along its galactic orbit. This distance can be derived through simple calculation: 220 kilometers per second, approximately 31.56 million seconds per year, equals 315.6 billion seconds over a millennium. The total displacement is 220 kilometers per second multiplied by 315.6 billion seconds. The result is approximately 694 billion kilometers. For easier comprehension, we can simplify this to roughly 7 billion kilometers. What does 7 billion kilometers mean? Neptune, one of the outermost planets in the solar system, has an orbital radius of about 4.5 billion kilometers. This implies the distance the solar system travels in 1,000 years exceeds the diameter of Neptune's orbit. It is sufficient to span the entire plane of the solar system's planetary disk. Now the probe's journey begins. Following its calculated trajectory, it flies toward Earth's predicted position 1,000 years hence. It traverses interstellar dust, schemes past star systems, traveling at near light speed. After a full millennium of arduous travel, it finally reached its target coordinates. Yet there, it saw no blue planet, no sun, not even any significant celestial bodies. Only vast, empty interstellar space lay before it. Occasionally, faint starlight flickered from distant stars. Where was Earth? Where was the solar system? They had already advanced 7 billion kilometers in the Milky Way's rotational dance. This deviation distance far exceeded any probe's effective search range. Even if this probe immediately adjusted its direction and scanned with optimal efficiency, the chances of locating Earth in such vast interstellar space were minuscule. It's like you booked a table at a seaside restaurant a year in advance, only to arrive on time and discover the entire restaurant has relocated 70 kilometers inland, with no updated address in hand. This scenario accounts solely for the solar system's orbit around the Milky Way. Add the galaxy's own descent toward the supermassive black hole at its core, alongside the vast spatial stretching caused by cosmic expansion, and this positional deviation becomes exponentially greater and utterly unpredictable. This thought experiment clearly demonstrates that, in the face of the cosmic chasm of spacetime, any navigation attempt based on past information is doomed to be a blind shot at a moving target. The endpoint reached by the probe will almost certainly be a void of nothingness. What it brings back, besides cold cosmic dust, is a profound understanding of the dynamic nature of the universe. The golden record carried aboard our Voyager spacecraft, which recorded Earth's location information, is fundamentally the same. Even if an alien civilization intercepted it, they would obtain only a long obsolete coordinate from the past, a historical monument pointing to where we once existed, rather than a tangible destination to reach. Within this dynamic cosmic labyrinth, all precise calculations and noble intentions may ultimately dissipate into the infinite stretching of space and the delay of time, leaving only eternal silence and missed opportunities. According to Einstein's general theory of relativity, mass distorts the surrounding fabric of spacetime. This distortion alters the path of light rays, acting like a gigantic cosmic lens. This is the gravitational lensing effect. It transforms the universe into a hall of mirrors filled with optical illusions. When light from a distant celestial object, such as a galaxy or quasar, passes through a massive foreground object like a galaxy cluster before reaching an observer, these rays are bent by the gravitational field of the foreground object, resulting in distorted, magnified, or even duplicated images for the observer. When the background object, foreground lens, and observer are precisely aligned in a straight line, we witness a perfect ring. This is the Einstein ring. as if the cosmos placed a ring upon that distant galaxy. When the alignment is less perfect, we observe distorted arcs, known as gravitational arcs, or multiple images of the same object. These are not illusions, but direct evidence of gravity reshaping spacetime geometry. Now consider a crucial question. If even powerful light from entire galaxies can be so significantly warped, what about Earth's faint radio signals? During their long interstellar journey, they traverse countless gravitational fields of stars, nebulae, and even black holes. Each time passing a massive celestial body, the signal's path is subtly deflected. A single deflection might be minuscule, but as the signal traverses thousands or tens of thousands of light years, after enduring countless such minute deflections, the cumulative effect becomes staggering. When an extraterrestrial civilization receives our signal, they analyze the direction of its arrival to reverse engineer the signal's origin. But what they deduce is the final arrival direction after the signal has been bent through a series of cosmic lenses. This direction may deviate dramatically from Earth's true location, may be vastly different. This deviation could span several light years or even tens of light years. Imagine, you stand at one end of a room filled with prisms of various shapes. At the other end, someone holds a flashlight. Light passes through these prisms and reaches your eyes along distorted paths. You judge the flashlight's position based on the direction of the light entering your eyes. The position you point to might be far from the flashlight's actual location. For an extraterrestrial observer, the universe is that vast room filled with gravitational prisms. Earth is that faint flashlight. The coordinates they map, based on the direction of the received signal, could very well point to a void beside us, complicating matters further. The distribution of mass in the universe is not static. The celestial bodies acting as gravitational lenses themselves are in motion. Thus, the deflection of signal paths also changes over time. This means coordinates mapped by an alien civilization may not only be inherently incorrect, but the nature and magnitude of their error are constantly shifting. The gravitational lensing effect introduces a layer of error that is nearly impossible to fully correct. It implies that even if a civilization receives our signal, they might be searching in the cosmic funhouse mirror for the wrong clown mocking them. Every declaration we send about our location, as it travels across the cosmos, may have been quietly altered by gravity's invisible hand, changing its delivery address. When we speak of matter in the universe, the stars, planets, and galaxies we observe are merely the tip of the iceberg. Up to 85% of the universe's matter remains invisible, collectively termed dark matter. Dark matter does not participate in electromagnetic interactions. It neither emits light nor reflects or absorbs it. We cannot observe it directly through any telescope. Yet its gravitational effects are ubiquitous, profoundly shaping the structure and evolution of the universe. By observing anomalies in galaxy rotation curves, the motion of galaxy clusters, and the formation of large-scale cosmic structures, scientists are convinced of its existence. It forms an invisible web enveloping the entire cosmos. This dark matter network exhibits a complex filamentary structure. Massive filaments connect galaxy clusters and superclusters, while vast, empty cosmic voids lie between them. Galaxies cling to this invisible web like dewdrops, distributed and moving along filamentary structures. Our Milky Way galaxy is embedded within a vast dark matter halo. The boundaries of this dark matter halo extend far beyond the distribution of stars in the Milky Way. Its total mass may exceed 10 times that of all visible matter in the Milky Way. Now consider the implications of this dark matter web for interstellar navigation. Any signal or object departing from or heading toward Earth must traverse this ubiquitous gravitational web. As they journey through interstellar space, the gravitational fields generated by dark matter filaments may appear feeble individually, yet collectively function like countless invisible highways, subtly altering the trajectories of all objects crossing them, whether photons, neutrinos, or future interstellar spacecraft. Their paths are subtly deflected by this gravitational web. For an extraterrestrial civilization attempting to locate Earth, this presents an unsolvable puzzle. They can precisely calculate the gravitational influence of all visible celestial bodies, but cannot accurately determine the distribution of dark matter. For humanity still lacks knowledge of dark matter's precise nature and microscopic structure, much less map its precise three-dimensional distribution. This is akin to navigating through a game, where your map reveals only 15% of the terrain. The remaining 85% remains hidden, yet exerts invisible forces upon your vessel, steering it off its intended course. Under such circumstances, reaching your destination with accuracy becomes nearly impossible. Even if an extraterrestrial civilization received signals from our Voyager spacecraft, when they traced the signals back along their path, their computational models, lacking data on the dark matter gravitational field, would yield a source coordinate with systematic errors. This coordinate might again point to an erroneous void. Dark matter functions like a vast, invisible gravitational trap in the cosmos. It renders even the most precise navigation calculations fraught with uncertainty. It reminds us that the vast majority of the universe remains uncharted territory to us. Within this unknown web of gravity, any assertion about position may be nothing more than a fragile inference built upon incomplete data. Earth is not a silent planet. For over a century, we have been broadcasting our existence into cosmic space. From the earliest radio transmissions to later television signals, and then to deliberate messages sent to extraterrestrial civilizations, these electromagnetic waves traveling at the speed of light spread like ripples, spreading outward from the solar system into the depths of the cosmos. Yet these signals, bearing the imprint of human civilization, face far from ideal vacuum conditions. During their long journey through the vast interstellar space, they must traverse complex, interference-filled cosmic media. First is the adjacent interstellar medium, the diffuse clouds of gas and dust scattered between stars. Though extremely low in density, they are sufficient to absorb and scatter radio waves of specific frequencies. Like a gauze curtain riddled with minute pores, they blur and distort the light passing through. When signals traverse denser nebulae, this effect becomes markedly more pronounced. A vast molecular cloud can act like cosmic fog, severely attenuate or even completely swallow signals emitted by celestial bodies beyond. Beyond simple absorption and scattering, signals also encounter the gravitational lensing effect mentioned earlier. Radio waves originating from Earth traverse countless massive celestial bodies along their path, from ordinary stars to compact neutron stars, and even black holes with immense gravitational pull. Each time a signal passes near these bodies, the signal's propagation direction undergoes an extremely minute deflection. This deflection angle may be too small to measure, but when the signal travels for hundreds or even thousands of years, having undergone tens of thousands of such minute deflections, its cumulative effect becomes impossible to ignore. It's like a traveler walking across a vast plain. He believes he's following a straight path. Countless insignificant pits and mounds beneath his feet unwittingly divert him from his original course. After walking dozens of kilometers, he may have strayed several kilometers off course, for Earth signals traversing tens of thousands of light-years. This path deflection accumulated from countless weak gravitational fields can cause the apparent source direction upon arrival from its true origin by several light-years or even tens of light-years. Moreover, the cosmos harbors various sources of electromagnetic interference, such as the intense radio pulses periodically emitted by pulsars, or the immense energy released by active galactic nuclei. These powerful background noises can drown out Earth's faint signals or superimpose interference, making decoding the information exceptionally difficult. Therefore, when a distant extraterrestrial civilization catches a signal from Earth with their radio telescope, what they receive is no longer a clear, pure positioning beacon. Instead, it is a distorted call that has endured countless trials, absorbed, scattered, repeatedly deflected by gravity, and intermingled with cosmic noise. The coordinates they calculate for Earth based on this distorted signal are fundamentally unreliable. These coordinates might point to an innocent star next to our solar system, or to a vast expanse of empty interstellar space. The cosmos is not an ideal medium for signal transmission. It resembles a noisy hall filled with interference and distortion. Our whispered self-introduction, after traversing this hall, may have become unrecognizable, hard to decipher, adding another impenetrable layer of fog to interstellar search and communication. The calls we send out, by the time they reach distant listeners' ears, may have long lost their original direction. In science fiction, wormholes are often depicted as space-time tunnels linking distant points in the universe, the ultimate shortcut for faster-than-light travel. Theoretically, wormholes represent a special solution to Einstein's field equations. By warping the geometry of space-time, they connect two points potentially separated by millions of light-years at a higher dimensional level, forming a bridge through which matter can pass. This sounds like the perfect solution to traverse the vast distances of the cosmos. Yet even this theoretically feasible ultra-advanced technology faces a fundamental paradox from the dynamic labyrinth of the universe. The core of this paradox lies in constructing a stable and usable wormhole requires an extremely demanding prerequisite, namely, precise knowledge of the exit's spacetime coordinates, not merely its spatial location, but also its exact temporal point, because according to general relativity, spacetime is an indivisible whole. You cannot specify a spatial location without considering time. Now let's place this technical requirement within the dynamic cosmic context we've been discussing. An extraterrestrial civilization seeks to establish a wormhole exit near Earth, enabling their civilization to arrive instantaneously. To do so, they must first obtain Earth's precise current spacetime coordinates. Yet, as demonstrated throughout our preceding chapters, this is precisely an impossible task. What they observe through telescopes is Earth's past. The radio signals they receive point to a past location distorted by light-speed delays, gravitational lensing, and dark matter effects. The future location predicted by their celestial mechanics models is fraught with immense uncertainty due to the complex motion and expansion of the universe. They lack the most critical piece of information, namely Earth's precise spacetime address. At this very moment, the present, this creates a logical deadlock. To establish a wormhole exit near Earth, they must first know Earth's precise current location. But to know Earth's precise current location, they seemingly need a wormhole that could instantly transport them there and conduct on-site measurements. This paradox resembles a key locked inside a box, where the key to unlock the box is the key itself. We may term this the coordinate a priori paradox of wormholes. Any method of faster-than-light travel relying on precise destination coordinates whether through wormholes or other theoretically possible means, cannot circumvent this fundamental issue. You cannot reach a place you cannot precisely locate. Even if a civilization mastered the astonishing technology to create and stabilize wormholes, they would still need to first transport a beacon or construction module to the target location via conventional sublight means. But this brings us back to our original problem. Delivering a beacon at sublight speeds takes an immense amount of time. By the time the beacon reaches the intended coordinates, the target will no longer be there. Attempting to compensate with dynamic predictions is futile, because the dynamics of the universe are too complex, involving too many unknowns and unpredictable factors, such as the precise distribution of dark matter and local variations in cosmic expansion. Any prediction inevitably fails over extended timescales. Thus, wormholes are not a universal key capable of forcibly opening cosmic doors. They resemble instead a precision key requiring perfect alignment with its lock. If we remain ignorant of the door's precise location and form, even the most exquisite key, it would ultimately have nowhere to fit. This paradox profoundly reveals that the physical laws of the universe seem to erect barriers at every level, from the fundamental constraints of relativity and the speed of light, to cosmic expansion and intricate matter distribution, collectively maintaining a state of fundamental isolation, making direct contact between interstellar civilizations a theoretically intractable dilemma. Beyond wormholes, another renowned superluminal concept is warp drive, whose theoretical prototype stems from Mexican physicist Alcubierre's 1994 metric. In this model, the spacecraft does not actively propel itself through spacetime, but achieves motion by altering the geometric structure of the surrounding spacetime. Specifically, spacetime behind the spacecraft is violently expanded, while spacetime ahead is extremely compressed. The spacecraft rides this wave of spacetime forward, much like a surfer riding a wave, since the spacecraft itself resides within a flat spacetime bubble. It does not violate relativity's constraint that objects cannot exceed the speed of light within their local space. It is spacetime itself that carries it on a superluminal journey. This concept ingeniously circumvents the light speed barrier, yet it faces a fatal prerequisite similar to wormholes, namely precise knowledge of the destination's spacetime structure. Warp flight requires precisely compressing the spacetime ahead of you, while simultaneously expanding the spacetime behind you. But this raises a fundamental question. What lies within the spacetime you intend to compress ahead? If you possess no knowledge of the destination's spacetime structure, warp flight becomes akin to a blindfolded leap into a deadly minefield. You might compress the spacetime in front of a star or even a black hole, causing catastrophic gravitational focusing effects, or crash headlong into an unexpected dense nebula. Even if you successfully avoid these conspicuous celestial bodies, the distribution of dark matter, pervasive throughout the universe and difficult to precisely detect, will introduce unpredictable disturbances as you compress spacetime, distorting your course. The more fundamental issue lies in warp drive still needing to answer that most basic question: where to fly. The basis for setting your course remains those Earth coordinates, which may carry enormous errors due to light speed delays, gravitational lensing, and cosmic expansion. You fly at warp speed to a location calculated from information millennia or even tens of millennia old, and that location is now long since empty. Warp drive might swiftly deliver you to the wrong place. It solves the problem of speed, but fails to resolve the fundamental dilemma of navigation. In a dynamic universe where every reference frame is in motion, and all coordinates are drifting, the absence of real-time, precise destination information, any form of travel, whether subliminal or faster than light, is destined to be an adventure with uncertain outcomes. The warp drive, this theoretically faster gun, still struggles to hit its moving target across multiple dimensions, due to the absence of a reliable sight. While we exhaust ourselves calculating all the physical barriers to interstellar travel, a more fundamental possibility often escapes our notice: that an advanced civilization capable of interstellar travel might fundamentally have no interest in seeking us out. Consider Earth's resources from this perspective. For a civilization capable of harnessing stellar energy, or even constructing Dyson spheres, Earth's resources are almost negligible. Water is not a scarce substance in the cosmos. Many icy moons like Europa contain liquid water, potentially dozens of times more than all Earth's oceans combined. Metal ores are even more abundant. The asteroid belt between Mars and Jupiter holds reserves of iron, nickel, cobalt, and other metals, sufficient to satisfy the massive construction demands of an interstellar civilization. As for energy, the power directly accessible from a star exceeds the combined energy of Earth's entire biosphere and crust by trillions of times. To a civilization commanding such orders of magnitude in energy, Earth appears as a speck of dust beside a highway spanning entire continents. It may exist, but scarcely warrants the effort of slowing down. Beyond the insignificance of material resources, a deeper perceptual divide may exist. We humans are accustomed to perceiving the universe through electromagnetic waves, namely radio and light, and naturally assume other civilizations do likewise. But a civilization millions of years older than ours may have long transcended this stage in how it perceives and understands the cosmos. They might construct images of the world through gravitational waves and neutrinos, or directly sense the subtle fluctuations of dark matter networks. Within their highly evolved sensory systems, the television and radio signals humanity proudly broadcasts might appear as faint as background noise, as primitive as cave paintings, barely worthy of recognition as an attempt at intelligent communication. Much like a bustling colony of ants on the ground, exchanging complex messages about food and nests through pheromones. A passing human might notice the ant's presence, but would find it nearly impossible and utterly uninteresting to decipher the precise meaning of their pheromones. The gap in perceptual dimensions between these two civilizations may be far greater than that between ants and humans. Such an immense disparity could foster a profound indifference. We have been listening intently across the cosmos, awaiting a response from the stars. Yet perhaps those more ancient civilizations are communicating in ways we cannot comprehend, exchanging messages we cannot detect. All our signals are like writing on paper and expecting deep-sea whales to read it. The medium and level are both wrong. So when we ponder the Fermi paradox and wonder why the universe is so silent, the answer may not be that they cannot reach us, but that they do not wish to come or simply do not notice. The silence of the cosmos may not stem from the barriers of distance, but from the vast chasm between civilizational tiers and our utter insignificance within the cosmic resource map. This is a humbling realization. We may not be protagonists on the cosmic stage, or even supporting players, but merely a tiny existence quietly growing, and destined to fade away silently in the vastness of time and space. This realization strips away the illusion of anthropocentrism, yet brings a unique kind of tranquility, allowing us to examine ourselves more objectively and our true place in this indifferent yet magnificent universe. We have traversed layer upon layer of obstacles through the dynamic labyrinth of the cosmos, from the coordinate cages of relativity to the eternal rotation of the Milky Way, From the delays of light speed to the expansion of space itself. From the illusions of gravity to the spiderwebs of dark matter. Ultimately arriving at this simple yet profound answer. All seemingly complex astronomical puzzles point to the same underlying cosmic logic. Motion is absolute. Stillness is but a partial, fleeting illusion. This is the very point that prevents interstellar civilizations from meeting. The cosmos, from the very roots of its physical laws, preserves the distance between civilizations. This realization brings not despair, but a peculiar sense of release and tranquility. In this boundless, dynamic spacetime, each civilization resembles an island adrift in a dark ocean, naturally separated by vast, profound seas, forever gazing into the distance, forever existing within its own realm. Now withdraw your gaze from the vast depths of the cosmos. Feel the solid ground beneath your body as it meets the bed. Feel the steady rise and fall of your breath within your chest. Our Earth, this minuscule existence racing through the motion of multiple universes, has become the safest sanctuary, carries us through the Milky Way, while shielding us from all the fury and chaos outside, maintaining just the right temperature for us, providing everything life requires. In this eternally moving universe, it is our one and only stationary reference point. Imagine this blue planet floating in the profound depths of space, like a meticulously designed arc of life. Outside lies a vacuum nearing absolute zero, deadly radiation, countless celestial bodies hurtling at immense speeds. Yet within a warm atmosphere, liquid water, thriving life, the cosmos, through its physical laws, has crafted a perfect isolation zone for us, allowing us, amidst endless darkness, to exclusively inhabit this vibrant oasis. This isolation is no curse, but a precious gift bestowed by the universe. Now let this sense of protection fill your entire being. Know that in this vast cosmos, a corner exists solely for you. Here you may lay down all guard, release all pressure, for the laws of the universe have set the safest boundaries for you. Feel your body gradually relax, from your toes to the crown of your head. Every muscle releases tension. Each breath carries away distracting thoughts. Your mind begins to drift away, like starlight traversing endless time and space, finally arriving gently at your eyelids. On this solitary island in the cosmos, there are no goals to chase, no distant shores to reach, only the stillness of this moment, only the serenity of the present. Let this cosmic solitude transform into the deepest peace within. Earth carries you, sailing quietly through the Milky Way. The moon stands faithfully by your side. The entire solar system moves in its rhythmic orbit. You need do nothing. Simply trust this grand system. Let it carry you. Let it protect you. Now let your awareness gradually fade, like distant starlight dissolving in the dawn. All thoughts, all questions, can be set aside for now. In the embrace of the cosmos, you are safe. You are protected. With each breath, sink deeper into relaxation. The outer cosmos still moves, expands, transforms. But you know, on this small blue planet, in this night that belongs to you, all is peaceful. Let sleep envelop you as gently as cosmic darkness. Let dreams unfold as freely as distant galaxies. In this eternal island, in this corner silently loved by the universe, sleep peacefully.